Hi everyone, welcome to today's session. We're going to go over how a thought process that we left with in the last class, where neural networks is a universal function approximator. So we thought we'll use sine function as a basis to to understand it. So we'll talk a bit about how he went about doing it. Yes, please.
All right. Of course, I would like to start with a disclaimer, and that is my understanding of how this works is very limited. Allow me to say that. And excuse me. And as I keep saying, all praise goes to ChatGPT. All right. So, well, see, if you look at what Bhargav suggested, he wanted us to take a sine wave and then order a sine function, let me put it that way, and then add some noise to that to bring in some randomness, and then try to train it using a neural network. Well, before we started with adding some noise, but we junked that idea and we thought, let's try to train the sine function. So, of course, thanks to ChatGPT, we tried a few combinations. So the first thing we did was I think I have, if I haven't shared the workbooks, I'll share it later in the group. So the first thing we did was we generated a sine function from minus 2 pi to 2 pi that you can see that here. And then we used a neural network to train the data. So you had x, which varies from minus 2 pi to 2 pi. And then, of course, you have y, which is the sine of x. And then we trained it. Now, don't ask me how that exactly works. I have no clue. But what I do see is there are a bunch of parameters which I believe are hyperparameters that are fed into the model, one of them being the optimizer, and the other is the loss, which is mean squared error here. And another parameter that is fed into the model is the epoch. I believe epoch is something like the number of times you train the model. I didn't look up what exactly it means, but when I ran this, I saw that the loss kept decreasing. So I think it trains it once and then again until a point comes. Of course, in this case, the number of epochs is fixed at 100. So which is why if you scroll down, you would see 100 epochs there. And this, of course, is sorry, you just scroll down. And this is the loss function. Then, of course, the next part is prediction, where I fed the x's and x values into a function, predicted the y using the trained model, and then I plotted it. Briefly, this was initially done for 400 data points between minus 2 pi to 2 pi. Then I tried 4,000 data points. And then finally, give me a moment. Yeah, I also tried an out of sample. I think it's this, yeah, out of sample. So which means I would have trained it to work from minus 2 pi to 2 pi. But then when it comes to predicting, I tried to predict, I think I predicted from minus 2 pi to 3 pi, if I'm right, just to see how well it predicts beyond the sample that I trained. These are the results. I've shared it in the group. So the first is when we have 400 data points, it was okay, but it didn't do a fantastic job. It did a poor job at these two regions. And then with 4,000, it was much better in the sense it could exactly mimic the true value. And finally, when I looked for out of samples, I should have it somewhere. I think this one, not this one, sorry. I think this one. Here we go. Oh, this was for a different case where I trained it for, I think from 0 to pi, if I'm right. I mean, the point is the moment we go beyond the X values against which we had trained the model, I find that the prediction values are way off. Tried several scenarios, and in all cases it was way off. Now, at that juncture, again, it's a question for Bhargav, it's a question for the team as well, and it's a deeper question. I asked this question to myself, and I think I had an answer, but let me ask that question. The question is, Bhargav said that a neural network is a universal function approximator. Is that right, Bhargav? That's the term, right? Correct. So when I couldn't train this out of sample, it called to question that statement, whether it's truly a universal function approximator or not. So I kept questioning myself whether it's that true or not. And one way I satisfied myself with an answer, accepting that as a truism, is I said to myself, look, yes, it is, as long as I trained it for a certain range and I predicted for the same range, then yes, it did approximate. It did a pretty good job of approximating it. But then the fact is, the moment I go beyond the range for which I trained. So for example, let's say hypothetically, had I trained it from 0 to 15 pi, I'm pretty sure the neural network would have predicted the y values for any x between 0 to 15 pi. It would have done a pretty good job, right? But if I train it for 0 to 15 pi, and if I were to feed say 100 pi, and if it doesn't produce the right result, does that mean it's not a universal function approximator? Is that how I'm supposed to interpret it? I don't know. So I wasn't too certain, but since it's a truism, there are two possibilities. Either my training was wrong, or maybe my justification was correct, where yes, I didn't train it for a lot of values I should have trained it for, which is why it threw a value which was very different from what was expected. I don't have anything else to share apart from this. Over to you, Bhargav.
This is awesome, VC. Okay, can you go back to the code?
Sure. Which one? I'll pick up out of training one. Is that okay?
I mean,
anything. It's
whatever
all the
you
same.
train,
It's
like
all the
what,
same. It's pretty
like
much the
what,
same. It's just that minor
okay,
differences here
what's
and there.
input? Your input?
Okay, my input here is
Input
in
is
this
mhm,
0 to pi.
mhm.
That's the input. And I try to predict it from 0 to 3 pi. Of course, I trained it for 0 to pi. And if you look at the output, does a brilliant job from 0 to pi. But the moment I go beyond pi, it fails to
Ah,
predict.
yeah. Okay, so let's poke holes in your logic, right?
Mhm.
So you told you built for 0 to pi and you're trying to do it, right? and you built some model for it. Like what is one assumption that you're making that we can challenge here?
Uh, One assumption.
I mean, this is true for anyone. Any of you can answer. I mean, it's staring in the screen, so I'm just telling you. Like, I think people who are staring at you are either me, VC, and the code that's out there. So it's one of us.
That it's a universal, I mean, predictor.
Okay. Okay. Any other? Kyle, what do you think, Kyle?
Assumption.
Thing that does not know it's a periodic function.
A what?
It cannot predict the what we are expecting is a periodic function. Like it repeats
Okay.
again and again.
Okay. Okay. Periodic function. Vasavi, what do you think?
I don't know.
Abhinav.
Actually, we are taking the data only between the interval 0 to 2 pi.
Mm.
So, without the
Okay.
information about the other region, we can't.
Okay. Naveen.
What do I think is neural network? Like when they are predicting a particular thing, it identifies the patterns in it, but I don't think so it will work for long range. For an example, let's do the same thing on the image as well, right? You have certain class, when you predict it, it works fine. When you do give different images of the same limit, it works fine. When you go for a new class, it fails, right? So it limits on the higher bound, I guess.
Mm. Okay. So, so I've written three things. One is what Naveen told, which I'm going to conveniently ignore. We're not going to talk about it right now because we'll do it in its full. Like we'll explain what he told in some of the later sessions. The bigger thing that I see is in this cell 3, right? You're assuming that the architecture that you have given is correct, that it captures, that it's designed in a way to capture the functional form that you're expecting.
So when you say architecture, what do you mean by that?
It tells that you've built a model that has you built a sequential model. It's got one dense layer, another dense layer, and then a classifying layer. That's how it is done, right? So this kind we'll talk about this when we start learning neural networks. But
Good
for everyone,
question, Bhargav. Does this mean this is a 3-layered network? Is that what it's
no,
supposed to
it's
mean?
two layer. It's two deep layers. So two
Okay.
fully connected layers and then one classification layer. One input, two fully connected layers, and then a classification layer. That's how the model looks here.
Oh,
And
okay.
this kind of network is called multi-layer perceptron. And
Oh, okay.
you also used an activation of ReLU. So a good rule of thumb whenever you're trying to do is that this is what we did in the previous session. We go and try different models. While in a typical machine learning setup, you would go and try different model architectures, right? So you would, you would try different algorithms. You would do random forest, you would do gradient boosting, decision tree, logistic regression. Here you would do different model architectures. So this is called the architecture, where there is an input layer and two layers, and then there is a final classification layer. Instead of it, we now can start thinking about doing different kinds of stuff. So you could have played with the activation layer. You will talk later that why this could also be because it's probably memorizing a lot of the data. So how do we ensure that it doesn't memorize everything and is able to generalize? So it could also be that you might have to go modify the model. I'm not telling that like in this problem, I can tell you that what VC did is correct, that it doesn't generalize in a multi-layer perceptron model, it doesn't generalize outside the domain on which it operates. But this is a common, the one common thing is we need to go rigorously test it. So one is building the model. A practical tip is we rigorously test this when we deploy. So we need to have access to a lot of testing data that we can test input into this and see if it matches or not here, because we know the functional form we want to mimic. It's been easy to go and disprove on the ranges in which it doesn't work, and then, or rather the range at which it worked. In a typical setup, it's mostly trying different structures and intuitively thinking, does it make sense or not? So that's so one of the things I would tell is play with different activation layers, and maybe like, can we go over your ChatGPT prompt? Like, can you show me what you tried?
Or multiple. I don't think I have it handy now.
Mhm.
It suggested tan H.
Mhm.
I tried, it didn't work.
Mhm.
Then initially there was a suggestion that we can try a polynomial,
Mhm.
but then it usually works only when X is small, because I think they're trying to use the Taylor series,
Mhm.
and the approximation usually works only when X is small, right? It's
Mhm.
close to 0. Otherwise, the approximation doesn't work. So
Mhm.
I tried that, even that didn't work. Beyond that, there were very generic comments on how we can go and fine tune.
Yeah.
I mean, there was a suggestion on playing with this activation function,
Mhm.
and to be honest, I didn't know that this is a reference to multiple layers of the network.
Mhm.
I
Yeah,
wasn't.
every line is a layer of the network.
So which is the first layer? How do we interpret that? This is the first one, is it?
The first layer is your input. The next layer, yeah, that's the first layer. So it has 50 neurons.
Oh, okay, all right.
Each neuron does something what is called ReLU. We'll learn what ReLU is, but let's say that, like, ReLU is just a function where whatever the input does, whatever the ReLU active stuff is done,
Yeah.
and then yeah, maybe if you had done, yeah, worth looking into some
All
of
right.
these.
Okay, all right.
Okay, the so there are some interesting learnings from doing this, right? I want all of you to do this. One of the learnings is that it's not a classification model, it's a regression model. We'll talk about what these two things are, but in today's session. But the output is a continuous variable. The output is not 1 or 0. It's not cat or dog, right? The output is a continuous variable. It can be anywhere in the real line, and so it became a harder problem for it to optimize, right? Instead, if you had just built a classifier where it was able to do only within a small range, you'd have been able to make significantly more progress. A model, like, we would have figured out some version of the model that could have figured out, because your output is always going to be bound. And in real life, a lot of applications of neural networks, deep learning, is in the classification space. I just want to understand if there is a cat or a dog, and so I would be able to go, and so which means that my output domain is restricted, and so I would be able to build something and generalize. Does it make sense?
And Bhargav, one more thing. You asked us to add the noise, right? I mean, I tried adding the noise. The result is horrible, actually. We see. Can you stop
Yeah.
sharing or
Yeah,
can I
sure.
share?
I mean, you have to perturb it a bit. Perturbing means adding little noise. You should not add huge
No,
noise.
actually, I have taken help of ChatGPT only
Okay.
because
But
I
depends
mean,
on
this is very
plot
new
it,
to me.
plot your. Can
I
you
plotted already. See, this
plot
is
your?
how it is.
Oh, good. Okay. This should
And the
work.
result is something like this. These are
Hmm.
predicted values.
This is good. You just need more epochs. Yeah, this is good. Yeah, you're correct. You're getting something similar. How many epochs did you run?
10.
You
This
need
all I'm
more.
telling you. Even before I
Okay.
saw it, I told you had to run more epochs, right? Your model didn't finish learning. Look,
Okay.
look into, like VC has done really good, right? His errors are very low. Like your
Yeah.
errors probably at epoch 10 is still high. Come down at 10 epoch. Come down. You see, it's 0.14. Do you remember what VC's errors were?
No.
You didn't see
We
what
see.
it was
I think it was
0.03.
point
No,
zero
no,
something.
0.03,
Okay. Okay.
0.04. Yeah.
Okay.
Yeah,
It
yeah.
kept doing it. It went
But
to
Bhargav, again
0.03, then it picked
question.
up.
Shrisha, can you just share that screen?
Yeah. Sure. Where should I go? We see.
Go to that graph.
Grab. Okay. This one.
Bhargav, what sort of a function is this?
This sine wave, no, sine wave got,
No, why does it thicken?
because she's dead. She probably has generated 10,000 points.
No, because it's of noise. She
So the
added noise.
noise. Can you go up to where you generated the data?
Oh, okay, I understand.
Yeah.
Oh, okay, the same point is getting repeated multiple
No, it's
times, right?
random. Like, no, come down, please, Risha.
Yeah.
Line
This one.
line 3.
She have added a noise
Line
there.
3, she's added a
No,
normal.
I know she's added noise, but I mean,
Every data point is randomized, no?
yeah. So no, my point is, I think the same data point in terms of X is getting repeated multiple times, because if it's mere noise, right,
Correct.
wouldn't there be a one-to-one relationship between an X and a Y, right?
No, it's not. You're going to, yeah, correct.
But this is like the same X is getting repeated multiple times, and at each time there's a different
No,
quantum of
same
noise
X is,
getting added, right?
no, same X is not, no, good point, Vijay. No, it's not. Let's look into line 3. Okay, it's a good question. All of you should do this. Okay. So she's generating 100,000 data points. Okay. Now, in the 100,000 data points, the next line tells that so linspace tells that in this line, line is generated, so linspace means line segment. Okay, in this line segment that starts with minus 2 pi to plus 2 pi, in this particular range, generate num points here is 100,000. So generate 100,000 points. So it will do equally spaced points in the equally spaced 100,000 points in this continuum between minus 2 pi to plus 2 pi. Okay. And then,
Sorry, if you don't mind, correct me if I'm wrong. I think what she should have done is she should have created the random normal from minus 2 pi to 2 pi. Is that right?
no, she has done correctly.
0 to 0.1, is it?
No, she has done minus 2 pi to plus 2 pi.
No, I'm talking of the random one. Look at the random.
The
It's a-
random is, no, that is random. She's telling that for every single value, so for y value, what it does, this is called vectorized addition. For every single value of my x, so add a normal value. That's all it does.
I understand, but wouldn't that still be a one-to-one
It's
mapping
not
between X and Y?
correct. It's a one-to-one mapping to x and
But look
y.
at the graph. Does it look like one-to-one?
I will tell you why. Because if you're taking 100,000 data points between minus 2 pi to plus 2 pi, then the value is probably going to be very, very close to each other. And that's why you see, and sometimes the values are going to be less, sometimes the value are going to overshoot, and that's why you get the thicker one.
Oh, okay. So it's technically not thick, is what you're saying. It's actually, right? It just looks like it's thick. Am I right?
No, it is not at the same value.
It is not, right? Okay.
Because your x value is unique.
Okay. Which is what I wanted to know. To me, it looked when I looked at this graph, it looked like as though why don't you do one thing? Just make it 20 points. Let's see how it looks.
Let's see what. Yeah, sure. Yeah, the values don't
Shirisha,
end up here.
Okay.
make it 20 instead of 100,000. Make it 20 and plot the graph again. I want to see how it looks.
Line
This
3.
one, num points.
Yeah, yes, make it 20.
Okay.
Just run the whole code again, right?
Okay.
Forget the last function, but I want to see how it looks. Yeah.
Okay.
Let's scroll down.
Yeah. Okay. Because there are 100,000 points.
So this graph connects the points to show like a curve, is it? Is that so?
Yeah, correct.
Oh, okay.
You can
Because
go
for
up
20
and-
points, I should have just seen discrete.
No, you can go up and you can change it. Can you scroll up, please, Risha?
Mhm.
One
No,
minute.
figure size.
28.
The plot.
Figure size. Okay, here.
Yeah.
What should
Not
I
the
change?
figure size, a plot. I don't know what to change. Some plot. Just a plot, right?
That will just increase the size of the image.
Yeah, correct. How do I get this to be discrete instead of, because for
I think
20
you
points,
I think you just have to do plt.plot.scatter. Can you just write dot scatter?
PLT dot plot that, no.
Top. Third line. The fourth line. Yeah.
Here.
No. PLT dot plot. No, you already have it there.
Okay, here. Okay. Dot scatter. Got it.
No. Is it there? Oh, yeah, correct. Yeah, correct.
Correct?
Yeah, correct. Run it. Just run that bit.
Yeah.
No, it's giving some
Not
error.
2 minutes. Sorry.
It is just like adding. You could ask ChatGPT to instead of instead of doing it as
No. Okay, you should not do the scatter here. Instead of PLT plot, you should do PLT scatter.
yeah.
So instead of
Plot.
PLT plot, do scatter.
here. Okay.
Remove the plot. Yeah. Now do scatter. Yeah.
Correct?
Yeah.
Okay. I would have still loved to see a line there, but that's okay. All right. Okay.
Vijay, you want to see the line with the noise, right?
Yeah, the line. I would have ideally liked to see a line. You know how you do sampling, right? The discrete, the straight lines connecting the.
So what you have to do, you have to do 2 lines. Okay. So the first line, the first.
It's okay. I think no. My original confusion was when I saw the thick band. I was under the impression that for the same X we are getting multiple Ys, but that's not the case. It's just the visual thing, I suppose. All right, got it. Yeah.
Which I have pasted in the chat what you have asked for, right? So try with that. You'll get
Okay.
that.
All right. Sure. Thanks.
Yeah. Now this the same thing with the scatter line. In between, you'll get the red line, which is the actual value. So you know what is your error and stuff.
Okay. Yeah. All right. Okay. Bhargav, over to you. Did we lose him?
I think he'll be back, I guess.
All right.
VC, I have a question for you.
Mm-hmm.
VC, while you trying to plot the graph, did you arrive at it at the first time itself, or you received some kind of the graph didn't first it wouldn't have been fitted, or at the first itself it is perfectly easy? Did you do any parameter changes?
No.
First
I did.
itself it get fitted
No
to
changes to the parameter. I just stuck to what ChatGPT gave me and it worked. I was
Because
more concerned about the fact that it didn't fit beyond the range I had trained it for. That was my concern. I tried various combinations, but nothing worked.
Because I did it with a PyTorch. In that, when I adjusted the learning rate, the fitting of the curve changes. When the learning rate is very low, the curve fits perfectly. As the learning rate increases.
Sorry, what did you use? Say that again.
A library called PyTorch. That's library.
The one that I used was PyTorch.
No, it's not about PyTorch in a 10 seconds. VC, I have validated what you have tried. It went same for me as well, right? So just trying with different architectures.
Yeah, correct.
Hopefully.
Yep. perhaps.
Actually, which
But
is
So what?
sorry, go ahead.
actually which
So
is making me wonder is how did ChatGPT came to the conclusion of that architecture 51? Because I did it with 16, 64, 64, 1 and it didn't get it, I didn't get it correct at first. I did it manually. Then I went to ChatGPT, it perfectly give me the 50, 51 and it worked.
Because that's the consensus. ChatGPT is the consensus, right? It's like when we did our first project, it automatically chose to split the data into 80% training and 20% validation, right? So perhaps it's the consensus,
Actually, what
and
I
that,
have
that
been
throws
thinking
up
is
perhaps.
ChatGPT would have tried it a lot and lot of time and come to this conclusion. I think I was thinking at the back end
No,
this would be
ChatGPT wouldn't try. It doesn't try anything. Let's be very clear. At least my understanding. It's assimilated knowledge that is available on the web. I think that's what ChatGPT is in a way. That's my interpretation. It's not as if it's not a computational engine. It's not as if every
so.
little. I mean, at least that's how. It's not like somebody sat there and coded the neural network.
No. I was thinking like what the neural network now learns, like the ChatGPT would have learned by doing it itself again and again. I was just thinking some kind of
Okay, that
learning
way.
would be there.
Okay, we'll take this up. We'll do more of this later on, right? Let's move to the next part of today's session. Can someone summarize what we learned last week? Maybe Arun?
So last week on we just started with the machine learning part. So what is that machine learning is all about? So for me, the understanding was like if the from the data whatever is actually available with us, if we can actually recreate the function, which after that if you give any new input, it's able to produce the same kind of an output. So that is what we were actually discussing last week about that. And we just started going through the different data types. So what is that ordinal type? What is that other data types are there? So I think we just stopped there.
Okay, good. Uh, okay, we'll start continuing from there. So basic terminologies. Features. Features are the list of the inputs that you have. In our example of loan, we have age, income, year, ownership, grade. There is something that you want to predict. That's called target, also called as Y. So if you take 20 years old, the statistical learning thing that we talked about last time would all be using this term called Y. With features target X, Y. So if you write mathematically, X means input, your features, and your target, your output is always referred by Y. Nomenclature, if you have many features, then you would use a capital X. Target is always 1, so it's going to be a small y.
So x1, x2 is a vector, is it?
X, so X, no, X1 is a vector.
Yeah, x1, x2, each one of them is a vector, right?
X1, X2, X3 are all vectors.
Right.
Y1, Y2,
Scalar.
will all be scalar. Yes.
Right.
Yes. And together, it's a tuple, right? So it's all historical, means that it happened in the past. We have this data, and that's what we take. We have two, well, there are three paradigms, but I'll talk about two today. The other ones will cover maybe in month 2, month 3 of the sessions. The primary thing that you need to know is that there are two kinds of ML paradigms: supervised learning and unsupervised learning. Supervised learning would come with this tuple x1, y1, x2, y2, x3, y3. and it means that given a set of features, we also know historically what the y value was. Now we now go and then recreate the function that given this value of x, I get the value of y. That's what supervised learning is all about. Okay. Now my y can either be a categorical variable or a continuous variable. If my y is a categorical variable, it's called a classification model. If my y is the target that I'm going to predict is continuous, then it's a regression problem. We have done two kinds of problems. One is today what VC showed. The sign is a continuous variable because it's defined, it can take any value. It's still in a range, but it can take any value in that range. So it's a regression problem. In the previous example, we tried on Monday and last week that we've seen, where we had to predict the probability of default. So default is only 1 or 0. So that's a classification problem. So two kinds of problems that we have seen. Regression will define a continuous value. Classification can have two kinds of output. Classification can either be a 0, 1, or it can be many classes. It's not necessary that it needs to be only 2. If there are only 2 classes, it's called a binary classification problem. If there are multiple classes, then it's a multi-class classification. Within a value of within 0 and 1, I can also predict the probability of it, right? So the probability is bounded between 0 and 1, so I can also know probability in addition to predicting my entire class. So that's what it is. So let's start. So we have talked about features, target. There is some target function. We'll talk a bit more about. Yes, Arun, go for it.
I think this classification, the term is very familiar because we do means use it in day-to-day life. Okay, I just try to classify A. It means like this. This is tiger. This is fox, kind of stuff.
Correct.
But when you say regression, what is that? That word is actually itself is very not close to us. So why that word came out is that what we are trying to do in doing derivation.
Yeah, the history of the word is very interesting. It just came at a time when I don't know if you've heard about the term regressing to the mean. Have you heard of this famous term? Like suddenly someone goes and scores 95%. Person is an average student, suddenly goes 95%. Then tells that regressing to the mean, like will eventually hit 70%. Keeps doing test, will hit 70%. So that's called regressing to the mean, right? So there is some average that you go. The etymology of regression, I don't recollect on top of my head. I used to know. I don't remember the story, but I'll find and share it on the group where we can discuss it in the next class. But
yeah, we'll do it.
It's a term that's how statisticians have used for a very long time, and just that the idea stuck. Okay.
It is nothing to do with the recursive nature or something like that.
Yeah, I know the word has a lot more negative connotation in other parts outside machine learning, but in the field of machine learning, regression means that I'm going to the target I'm going to predict is a continuous variable. That's the target is going to be categorical, then it's a classification problem. We talked about this. I'll talk a bit more about all of this. What an H is, what an F, what an A. This screen, just remember this. We'll talk more about this in this screen, right? There is some God function which we don't know what it is, but it is generating some data. It's generating a lot of data in which we got access to a certain amount of data, which is your x1, y1 all the way to x and y1. Okay, we have some data.
Bhargav, question: how do you define x here in the God function?
Where is x? In which
I don't know what you call that X. What do you call that in the God
Yeah.
function? Yeah.
In this is a very statistical way of writing. It's telling that so this is like in my matrix there are different columns in which I know the domain in which each variable can be in. Domain in statistics, people would have read what is domain in statistics. Abhinav, what is domain?
Is it Bhargav, what we asked?
What is domain? In statistics, what is domain?
Domain.
You're like blanking, okay, but you're awake. Good. We see what is domain in statistics?
I wish I knew, but I think it's the range of values that
The range of values.
A domain
basic.
Excel.
no, it's the range of
X
values it
values
can
are
take,
called domain.
the complete range. So sometimes this can be the entire real line,
Can be that area.
right? Or if there are three variables,
Correct. For
each of
probability,
them can be real, then it's that R cube or something like that, right?
we'll talk probability. What is the domain of probability?
0 to 1.
0 to 1. For probability, it is 0 to 1. Right? So that's an example of a domain. Domain is the range of values from which something can be taken. Range in statistics also has this very specific definition. What is range? We see.
Y
Abhinav, go for it. Yeah.
the variable y's limit is range.
What is y's limit?
A range in which y can exist.
That is
Right.
range in it. That is domain. What is
Okay.
range? Hey, Naveen, what is range, Naveen? Explain to us.
Well, yeah, I'm here. It's let's say how wide your data set is spread.
Okay, correct.
I
Okay,
will means the highest value minus the lowest value.
highest value. Yeah, correct. So, yeah, Naveen's definition is correct. Yeah, it's the how wide your data is. That's the definition. Correct. So yeah, the formula for that is what Arun told. Your highest value minus your lowest value. But that does not necessarily mean that that is your domain, right? So here it tells that there is some domain of my data, it maps to another domain. It's mapped by a particular function. So I'm taking a matrix and I'm mapping a vector that's passing through a function that maps to a scalar. So there is a domain on which it exists and there's a domain on which it exists. That's what this particular line tells. There is some, but this transformation, some God function which we have no idea, we have no access to it, we have no, we have some clue to it, but we don't know what exactly it is. The only clue that we have is this set of training data that we have. Okay. So we only have access to some of the training data, not all of the training data. Okay. That is why it is called a sample. Okay. So the other, I mean, as much as like a lot of the fundamentals are grounded in statistics. So the other common thing from statistics is this concept of sample versus population. Population means that I have access to everything that is ever possible in that particular function, my entire exhaustive set of stuff. That's what population is. We never have access to the population in real life. All we have is a subset of it, which we call a sample. And so all that we have is that we can only observe a sample. So given the sample, the goal is to reverse engineer and find this God function. How are we going to do that? We are given with the arsenal of different hypothesis set. Hypothesis set is the set of algorithms that we can try. We talked about it, different algorithms that can exist in random forest gradient boosting, decision tree, linear regression, and within each one of it, you can change your hyperparameter. So every single thing is a model by itself. And then there is some learning algorithm that will help us arrive at what is called a final hypothesis. We can only have a hypothesis. We can only have a conjecture, a guess on what the God function is, which is G, which we think approximates to the God function F. That this is the theory of machine learning. Okay. In a typical machine learning class, they'll never teach this, but this is the, like, if you take hardcore mathematical introduction to machine learning, this is like pretty much the first session that they will start with, which talks about the theory of machine learning. This is why machine learning works. We gave a textual representation of it last week, because there we know that, what did we start? We started telling that a pattern, the essence of machine learning, right? The pattern exists, and if we'll be able to go and do it. What it internally mathematically tells us that there is some God function, and then we are able to see some sample of it, and we have an arsenal of hypothesis set in which we can successfully use some learning algorithm to finally conclude with some G, which using the learning algorithm will approximate to F. Now there are still two big things. One is, what is this learning algorithm, and how do we arrive at the final hypothesis? Two things that is not yet said. We'll talk about it in the next slide. But any questions on this?
Bhargav,
Hypothesis set is different from learning algorithm, right?
Correct. Hypothesis set is like, so think of this like a query we're keeping there. I can have a bow and arrow. I have like a bunch of weapons that I have. Like, all these are hypothesis sets. I can either use a linear regression, I can do a logistic regression, I can do a random forest. In a random forest, I can do different hyperparameters, and everything is a separate hypothesis. So that's what hypothesis set is. Hypothesis set is my entire collection. So in general, this is infinite, right? There's like infinite set of algorithms that I can throw into my particular training data.
But Bhargav, question: the learning algorithm is also closely associated with an individual element in the hypothesis set, right?
No.
So no. So if my hypothesis set is, there are 5 different hypotheses, then wouldn't the learning algorithm for each one of them be different?
The learning,
Or would it be?
yeah. So the learning, how everything learns is correct. Okay. Sorry. How do we select like? So yes, like what learning in a linear regression is very different from learning in a decision tree. Correct. Yes. Correct.
So it's almost like a one-to-one relationship between the hypothesis and the associated algorithm, isn't it? Which, in a way, right? No, because there's nothing like a God. There's nothing like a one fit algorithm for every single hypothesis. All sizes.
There is. Yeah,
okay.
Internally, okay. Okay. I'll take a pause here, and then let's think through this. Right. My hypothesis set. Let's say. Okay. Let's stop sharing. I will. 1 second. Let me share my screen. Man, this one is struggling to work with. Why? Okay. I have this particular value. Okay. How do I go about doing something like this?
No, but is this, you've already figured out that this is the hypothesis, correct?
I'm already defined this is my hypothesis. Let's start.
And there is only one hypothesis here.
Let's start with this hypothesis.
Can we say that?
And then build it over it.
Yeah. Right.
How
so I'll run a linear regression algorithm.
That's okay. This is a linear regression algorithm. This is linear regression. What is the
my point is, this is your hypothesis, isn't it? That
this is my hypothesis.
the God function is y equal to mx plus c. correct?
We don't know. We assume that this is what it is.
Correct. That's the which is why we call it a hypothesis, right?
Correct. I am hypothesizing that this is how that my data is linear. That's what
correct
function is.
and
Now,
and it's in one variable again. That's that's part of the hypothesis.
Variable. I need to find what do I, so now this is all known. Y is known, X is known. My learning is I have to find M and C, right?
Right.
That's what I have to do. Like think of this like some puzzle, right? I have Y equal to mx plus c, M I don't know, C I don't know. I want to find M and C. Okay, which means that learn M and C, which is what I want to do, right? Correct?
Right.
Yeah. Now your question is, how are we going to learn? How are we going to learn this?
Using a learning algorithm, say the linear regression.
Yeah, okay.
So I have the training data set, I'll pass it to the model and then figure out.
How will we do that? Tell me. Correct. What is the learning algorithm here?
Least squares.
People won't know. Okay, what is least square?
Okay, I'll okay.
I mean, for me, it's like any algorithm. Okay, where we are saying is like we are going to
I'll try to fit a straight line using y
give
and
data
x.
one by one to the algorithm. We are actually giving something to that one, and then say from that it actually tries to means like create that particular line or something like that, right?
I'll let me put it this way. What I'll do is let's say hypothetically I plot all this y and x.
Correct.
Right.
That is literally what I'm going to do.
Correct. And then I'll try fitting straight lines and see which line comes closest to the data points. That's the whole idea of least squares, right? So I'll have a measure to determine the distance between the points and the straight line. One of them could be the norm or whatever.
Which is what I want. Okay. So I want to find what it is. So I'm going to, I'll tell you how exactly the learning algorithm works on this particular linear regression model, which is on two variables. I have y equal to mx plus c is what we think. This is where the data is. I'm going to assume some random value of m and c. Okay, let's say at that particular point, the line will look something like this for you. Okay, let's say the line looks something like this. Let's say this is my initial model, right? There is no science behind it. It's randomly generating a value for m and c. And then what we're going to do is that I'm going to find the distance between, for every value, I know what the distance is, right? I know, like, we can find the deviation between where it predicted. So this is the predicted value, this is the actual value. I can find the delta between all of it, right? I can find my value between y and 2. So this is probably 1, this is probably 0.2, this is probably 3. I can find all of it, right? Now, what we're going to do is that we're going to go and then we're going to take the, so for all of it, we're going to square, this is called deviation. So this is what I want, but this is where the difference is, right? This is called square the deviation. So now I will square the deviation and then I will go and then I can go sum it up and then I can take, like, say 1, 2, 3, 4, 5, 6. I can get 6 values for 6 square of the deviations, and then I take the average of the 6 deviations. That is called mean square error. Okay, that's the term that VC started with. So I'm going to do mean square error. Now my optimization function here is something that many of us have learned but maybe don't fully understand. It's something that we learned in calculus, that my goal right now, I want to use a more technical term, my objective right now is to go and then minimize this, right? This is what I want to do. Like I'm finding this delta everywhere. This delta can be, for some it's okay, for some it's high. I want to go and then minimize this. Now, how do I go and minimize something like this?
Was it a question?
No, it's a question, yes.
Okay, calculus. So calculate the derivative.
Derivative equal to 0.
Derivative equal to 0. It's a brilliant question, brilliant answer. Derivative equal to 0 will give me what? Minimum or maximum?
Concave.
It will give both maxima and minima. The second derivative has to be
Okay.
wait. Should be one of those,
Second
either
derivative
positive or
will
negative.
give us-
But question, that's a closed form solution, right? Is that how the algorithm works?
Correct. So, brilliant question. Okay, it's a closed form solution. So we will
Actually-
approximate everything to a closed form solution. Okay. So now okay, let's come back over here to talk about somebody. So
Is it question? Does it do something like a gradient descent to figure out?
Oh, we'll come. We're jumping the gun. Wait.
Okay. All right.
Come there.
Okay.
Come there. We'll come there slowly. Okay. But even before we do the first derivative to do something like this, the first derivative will be built on some function, no?
On M and C.
On
Right.
what?
M and C.
Derivative is done on M and C, is it?
Because that's the variable, right here.
No.
The
When
error
we see
function.
constants, right? The derivative of constant will be 0.
No. If you have the data point, derivative. Okay, now what's the? I still don't understand what is MS. How will MSC? Is MSC even a function here? It doesn't even look like a function, right? Because you've just drawn a straight line,
Correct.
which is fixed,
And then I have.
and MSC is fixed in this case because the straight line is fixed.
MSC is fixed for this particular value of M and C.
Correct.
Right? This is some random value.
So how can I minimize that?
You cannot.
Unless you define that
Correct.
line
So that's
as
why I
some
need
M1 and C.
So what is my MSC here?
The
What is my
error.
MSC
Sum
equation?
of the errors.
Okay, y minus y hat whole square, something like that. Okay, or take a y, which is actual value, minus the predicted value, square it. Divide by the number of data points.
And that's okay. That's
right. And the predicted value would be, again, if we have an equation,
y minus
that
whole square, and I want to minimize
of
this.
Of course, divide by n.
That's okay.
So it doesn't really matter because if you minimize the numerator, should be sufficient.
Okay. Yeah. Like okay.
Y hat, of course, is
what I want to do.
It's a predicted function, so it's like m plus mx plus c, right? Essentially, right? Where x is the input value. So this would be an equation in M and C, isn't it? Effectively.
So you would do a partial derivative on your weights.
M and correct. M and C.
Effectively. Partial derivatives to then understand where it is, right? So if you do it, then you can minimize it and you would be able to figure out what the minimum values, like when you set it to 0, you'd be able to find what is a value for. So if you want to find a value of M, if you want to find a value of C, that's how we would go about doing it. Now, the fascinating problem we have specifically in computer science is that this is all like, so we talked about, VC brought up a good concept called gradient descent, and not like we already know that I can do my first derivative, set it to 0, and then do it. So this particular function that you see 1 over n y minus y hat whole square, what will be the functional form of it? When you plot, how will this look like for various values of y and y hat?
Parabola.
It's a parabola. Do everyone agree? Like you all would have learned y equal to ax square is the functional form of parabola. You probably learned in, I don't know, 8th, 9th, 10th. I think I learned in 8th or 9th.
Origin will be moved.
What?
In the case of y minus y1 square, the origin will be moved somewhere.
Y minus y1 square? Origin will be?
No, he's not asking that.
Origin will
He's
be
asking the
moved.
functional form, Bhinav. Bhargav was asking the functional
How
form
will
of
the
this
function
equation.
look like? If you plot the function, how will it look like?
I mean, imagine y hat to be mx plus c, where x is given, y is of course given. So which means it will be m square and c square. So it doesn't looks more like a parabola, right?
Yeah.
At least.
It will look like this.
Yeah.
It will look this nice. More like this. Smooth curve. Okay. Done. That's how it will look like. It's a, I mean, probably a homework. Go read about parabola. We all learnt in school. There's nothing that we ever will cover that's not taught in school. Okay, everything stops at 12th standard mathematics. That's all. But this is a function. It's a parabola equation. A parabola is unbounded on the top. It only have a minimum. The maxima is, it doesn't have a maxima. It's unbounded. So every time when we define the loss function that we want to work with, the loss function is something that we define here, for example, as mean square error, would always be in some form which has a minima. So it'll be a smooth function. It's not necessarily always need to be a parabola, but it'll be a smooth function and will have one strict global minima. This is super important. Okay.
Bhargav,
D.
sorry, one question.
Yeah.
Here we have in U format, right? What if it is an N? Can you draw that? Is that a parabola or not a parabola?
So you're
I
telling
totally forgot.
like
Yeah,
this,
where we have one maxima. Yeah.
It is, but if you look at it, Shirisha, there's a squared there, right? So it will
Yeah.
always be positive. The minimum value of a square can be 0.
Okay. Yeah.
Right? Which is why it's a parabola that looks like a U and not an inverted
even
U.
this can be distributed, right, across positive x region. So in that case, it will have maxima. It's not only minimum.
No.
What I'm trying to say.
No. Okay. X, when we say maxima and minima, we are talking of y. MSE is plotted on the y-axis.
Correct.
Right? So if it's plotted on the y-axis, then you can't have a minima. I mean, you can't have a maxima when it's a squared function, right? How will you have
we can have, right?
How?
See, I have a parabola like in that n format distributed. Okay, n can never be negative. Okay, so y is never negative.
No, the squared can never be negative. Any squared number.
What
minus 5 square is 25. 5 square is also 25. Correct?
So yeah, let's say it is distributed only in first quadrant, Q1.
Yeah, sure. It doesn't matter where it is.
Then we can have the above curve also, right? Right from 0 to infinity.
That's not how parabola will look like, right? Parabola is symmetric. All parabolas are symmetric. So your thing would come when I have a very large positive number, y equal to ax square plus some plus c, some very high number, so that I'm always on my domain is still in the first quadrant. Even then, the parabola is always symmetric.
Okay.
Shirisha, do one thing. Draw whatever you had in mind, send it to the group. We'll discuss.
Okay, sure. I'll do that.
Right?
I'll do that, please.
Okay. So this is what we do. Unfortunately, computer does not, even in this day and age, does not have a way to directly compute the first derivative of it, and that's the way. So so derivatives are defined on continuous scale, right? The very definition of derivative is rate of change for a small value, right? And that's defined on a continuous scale. Unfortunately, computers are digital and it's only on discrete values. So you need to have an algorithm to compute derivatives. And because it's done in small values, and then my error form can be in multiple ways, we cannot go and then directly minimize it for a number of reasons. It's just not computationally tractable. And so we need an algorithm that can help us go down this path of this error. This is my error function, right? I want to go down this error path wherever I am. I want to find a way to go and hit this particular value. I need a function that can help me do that, which is what gradient descent does. Gradient descent is just a way of computing my first derivative. But instead of going all the way in, my gradient descent is a gradient is my first derivative, but I'm going to descend it slowly. So instead of going all in into my gradient descent, which computers are not computationally tractable, I'm going to take a very, very small step in the direction of my gradient until I hit there. So in the direction of my gradient, once I know my gradient, I can go and update my value. So initially we talked that it's m and c. We're going to take our first derivatives, partial derivatives with respect to m and c. I know that what is the value, the delta value that I should move in that particular direction. So as I keep moving, I keep modifying my value of m and c gradually. And then, so which means that by definition, this algorithm called the gradient descent algorithm, that's my learning algorithm, so my error will naturally be lower because I'm moving in the direction of my gradient. My gradient is the lowest error. My first derivative is the lowest point, but I'm doing it in a smaller direction, smaller steps, baby steps. So the next step I take, which is that m is perturbed by a small value in the direction of my gradient, c is perturbed in the direction of my gradient in a very small way. The next value of my y hat is going to be my summation of my mean square error is going to be lower. So it was this much, it's going to be lower. It's going to keep going until it hits the lowest particular point. That's what we'll keep doing until a point where the error, the MSE does not change across a few things. Or you can keep doing it. I'll keep doing it for 1,000 steps. Or if for 10 steps it doesn't change, then I'll call it telling that that's it. I've reached my minimum, and then I will do it. So that's how this is how the learning happens, and that's how the learning ends. All learning here means that I have a set of weights M and C, terms that you should remember, weights. I want these weights to be, I want to predict these weights. And to do that, I'm going to randomly start initializing some value for these weights. And then I'm going to find the gradient of it. I'm going to descend in the direction of my gradient. I'm going to perturb both the values, the weights a bit in the direction of my gradient. I keep doing it until I either hit the maximum iterations I want to do, which is a hyperparameter that I'm going to set, or it doesn't change for a very large, for a few iterations, it doesn't change. So then I know that I've hit my minimum. So that's what it does. Any questions here?
Bhargav, question. In this case, there are two weights, right?
The two weights,
M and C. So shouldn't this be a surface and not a two-dimensional parabola?
There are two.
The MSC.
Two-dimensional parabola, no, the error function is always, so yeah, It'll be three-dimensional. You're correct.
right? Because
We'll
you'll have
do it
M in one direction, C
M
in the
in
other
direction,
direction.
C in another direction, and then the error function is on that. Correct.
Correct,
For
right?
various values of M and C, I have to have a error function. So I don't know how to draw that. Yeah, no, you're right. That's how it will be. So it's going to be something like this. It's going to be like this. Oh man.
I mean, just imagine a hemisphere. That's one way to look at it, right?
I have no idea if we can draw like this.
I think there should be something easily available in Google.
Yeah. I mean, okay, fine. Wait, it looks something like this. Yeah, it'll look like this. Yeah, that's literally how it looks like. There is a slope. So there is, yeah, correct. This is M, this is C, and then for various values from M and C, there is something that goes on, and then the goal is to find the minimum value. That's how there will be some minimum value out here. Okay. Yeah. Good. This is the loss surface. Make sense?
So loss and mean squared error both are same.
Loss and
Mean squared error.
here mean square error is the loss function, right? Loss function will keep changing based on the algorithm.
Okay.
Okay. So here loss function is okay. Let's go back to the deck and see where we are.
Bhargav, I have one doubt.
Yeah, yes, go for it.
So I remember when we were doing this neural network paper, we solved problems and we were asked to stop when continuous epochs had the same output value. So is it like similar to this?
Correct.
Is the reason you told?
Yeah, so there are two ways. Either I can do it for n number of epochs, iterations, or if the value doesn't change for a number of epochs, like the concept of epoch is different in neural network. We'll come to it, but over here, assume that but very similar. Two things that you need to know: the number max iterations, either it hits or the value in two separate ones don't really change much. Okay. Consist of algorithm training.
But just to summarize, so the basic assumption or the axiom we are actually taking here is like there will be one global minimum, right?
Because
That's what
it will
that's
have,
what
because it is correct. So this kind of there's a special word when you have only one global minima. These functions are called convex functions. Convex will be like this. Parabolas are convex. We have learned in physics convex, concave.
yeah.
Convex functions. So every loss function that you will ever see in machine learning needs to be a convex function. So it's a mandatory requirement that if you have to define a loss function for your problem, it needs to be convex. Did we lose Arun? Arun?
No, I'm here.
Yeah, you're here. Yeah. Okay. It's literally what we just saw. We find the errors, we plot the errors, and then it's like literally what it is. We can do one-step learning, which is basically set it to 0. But we learned a bit about how gradient descent works. So that's what it is. I will stop recording.